an important aspect of planar graphs, and maybe one of the very first places in which they appeared, is in the context of map coloring. So the problem here was really the following, that when you try to draw the map of, let us say, a country which shows its various states, or maybe a state showing smaller districts and so on. So anytime you have a map on the plane of any country, typically what happens is that there are these subdivisions, right? So there are, which could be districts or whatever else, and these often have some very strange boundaries, right? So the boundaries between adjacent states may be in some funny shapes. So it's not it's not something we have much control over. So this of course depends on the actual political boundaries or whatever it is. So here is an example. Now when maps are actually drawn, the goal is to color these different regions in such a way that they are visually separate, right? So you want to give colors to each of these states or countries such that you can visually tell one apart from the other. So that's the usual problem of map coloring, something that you've probably seen in maps of India and so on, where different states are colored differently. So for example, if you give this state say the red color, then you want to avoid using red for each of its 3 neighboring states, right, the ones which share a border with it. So then you would sort of pick maybe other colors to color these guys. So if I pick green here, then I would want to avoid green for its next adjacent guy. So maybe I could pick green on the other one here, and maybe pick I don't know, orange or purple for this middle region and so on. So if you sort of try doing this, so this strange big thing I drew, so keep going this way, try to color the different regions using with different colors, subject to the requirement that no 2 adjacent regions should get the same color. So that's the main constraint, no 2 adjacent. So adjacent means the following: they should share some some reasonable boundary. If I just had 2 regions with just a point in common, then I don't think of them as adjacent. Okay, so no 2 adjacent regions should get the same color. So this is one of the first things you would want to do if you were trying to draw a map and color it. I mean, if you are trying to color the map of a country, for example. Okay, so try drawing various maps and seeing how well you can color it. So in this particular case, I won't do the entire thing, but so the goal also is to try and do it with the least possible colors, right? I mean, of course, if you had lots of colors available, you could just give different colors to each of the different states. So I want to do it in a very economical fashion. So that's the other constraint, using the least possible number of colors, least number of colors possible. So those are sort of the 2 rules of the game, and you can sort of try doing it for various configurations of maps. Okay, so this is the map coloring problem. Now it turns out that this can actually be phrased as a problem on graphs or planar graphs. So how do graphs come into play when you are trying to color maps? What you can do is to imagine so there is sort of a graph involved in this whole thing. So you sort of imagine that there is a dot, one for each of these states, and what you do is you join 2 of these dots if the 2 states have a boundary in common. So for example, here I join these 2 because there is that boundary there. So I draw an edge which sort of cuts the boundary somewhere. So these 2 have a boundary in common, these 2 have a boundary in common, these 2, and so on. So you can imagine how this graph is formed. So if I have a map, I also have a graph. and it is not too hard to see that this graph will turn out to be a planar graph, okay, because of the way I chose my dots and the way I am drawing my edges, I am drawing them to pass through the common boundary between them, will turn out that the associated graph is planar. Okay. So, there is a graph, so that is the observation here. So, there is an associated graph. Which is planar. There is an associated planar graph to this map, to each map, okay, to any map. Okay. So, that is the graph of the map if you wish. So, you can keep going like this. Every time there is a boundary between them, you join the main edge. Okay. So, now what does the coloring problem translate to? So, the coloring problem is really the following. So, I have got each region of my graph has to be colored. So, what I will do is I will say, okay, at the level of the graph, what is it that I am trying to do? So, if I give you a graph with certain vertices and edges, so let us translate this graph coloring to this map coloring problem into what we would call a graph coloring problem. And what is the graph coloring problem? You are given a graph with some vertices and edges. So, I am given G, which is V comma E, some vertices and edges, maybe something like this, and so I have edges between them. So, recall in the map case, if I had an edge, it is just saying that those two vertices, those two regions have a common boundary. Okay, and I know it is a planar graph in this case. So, I know that there will be a way of drawing it where the regions where they do not where the edges do not intersect. So, we have a graph like that. Okay, and so on. Now, given a graph, the goal is to assign to each vertex, you have to assign a color. Okay. So, a coloring, so here is a definition. So, an allowed coloring or a sometimes called a proper coloring. So, what is a proper coloring of G is the following: you assign a color to each vertex. Okay. Now, assigning a color to a vertex can be thought of as a function if you wish. What is it? It is a function from where to where? From the set of all vertices of the graph, from V, let's call it V, to the set of colors. So, imagine I have got on the other side, I have got a set which is say red, blue, green, etc., to a set of colors, or just to make it simple, I can just imagine my colors are the numbers 1, 2, 3 and so on. Okay. So, it is a function from V to the set with the numbers 1 to n. So, imagine I am going to use n colors. Okay. So, recall this set is what we usually denote by this notation bracket n. So, a proper coloring using n colors. Okay. So, sometimes we will call it an n coloring, just putting the number of colors in the definition. A proper n coloring of G is a function which assigns to each vertex a number from 1 to n, subject to the conditions. So, let us call this function f such that satisfying the following property, that if I have two vertices u and v which are connected by an edge, then f of u cannot be equal to f of v for all pairs of vertices which have an edge between them. U v which have an edge between them. So, for example, in this graph that I just drew, a coloring would be an assignment. So, I could assign, so here is an example of a coloring. I could assign the number 1 to this vertex, but then I can't assign the number 1 to the one next to it. Okay. So, I could assign the number 1 again here, because this one is not connected to the first vertex that I drew, I could do 2 for example, I could do 1 again, but let me do 3, I could do 2 here, 3 here. So, here is an example of a 3 coloring of this graph, because I have assigned numbers to the various, numbers are to be thought of as colors. I have assigned numbers to the vertices such that whenever there is an edge between 2 vertices, I do not give it the same color. Well, not quite. I gave this guy the color 3 and observe that there was this vertex which had color 3. So, since that had color 3, I can't give this color 3. Okay, so let me make this a 1 for example. Now, this is a proper coloring. Okay, because now if you look, if you look at each edge of this graph, the colors on the 2 ends are actually different. Okay, now the famous statement or theorem about planar graphs in relation to colorings is the following. So, this is called the Four Colour Theorem. It says if your graph is planar, it can be drawn on the plane. So notice that when I looked at the graph coloring problem, I could actually consider it for any graph, not necessarily for just planar ones. I could state the same definition for any graph. But when you look at graphs which come from maps, then those are necessarily planar. Okay, so the Four Colour Theorem is actually for planar graphs. So it says if G is planar, then it is always possible to just use 4 colors. If G is a planar graph, then there exists a proper 4 coloring of G. Okay, in other words, there is a function from the set of vertices of G to the numbers 1, 2, 3, 4, or to the set of 4 colors red, blue, green, yellow, such that you can assign colors to the vertices so that when 2 things are connected, they have different colors. So, in particular, it says that if you are drawing a map and coloring it, you can just use 4 colors to color the various states. So, in particular, it means, so this may be a corollary if you wish, in particular, any map on the plane can be colored just using 4 colors. Okay, so it's a sort of an interesting statement and sometimes sort of hard to believe, because you could have rather complicated configurations of states and one curving into the other and all kinds of crazy boundaries between them, but no matter what, it's always possible to just use 4 colors to color them. Okay, so you should try it out on various very strangely drawn maps and see if you can try to violate it, try to see if you can draw some crazy maps where you can't do it with 4 colors. Okay, the theorem says it's not possible. It's always possible to just color using 4. Okay, so this is a very famous theorem. It was conjectured around the 1850s, but proven only around 1976. The famous proof of Appel and Haken, which used partly used computers to decide some of the cases of the proof. Okay, so now if you take this 4 color theorem for granted, so just assume you are given this theorem, then here is a problem. Use the 4 color theorem to prove that the following 2 graphs are not planar. Prove that the following graphs are not planar. Well, by showing that they are not 4 colorable. By showing okay, so one of these graphs is the graph K phi that I showed you earlier. So you just draw the pentagon, 5 vertices with all possible edges between them. So, this graph is not planar, and try showing that you cannot color it using 4 colors. Okay, that is sort of easy. And here is another interesting graph. So, you draw 3 vertices on one side, 3 vertices on the other side, and you connect all vertices on the left with all vertices on the right. Okay, so this graph, sometimes called K33, again show that this cannot be colored just using. So, this graph is called K33, the complete bipartite graph. This cannot be colored using just 4 colors. Okay, and as a corollary, conclude that neither of these graphs can be drawn on the plane, no matter how hard you try. Okay.
In the assignments, we can also give like Peterson graph.
Absolutely. Yeah.
Without the Peterson graph. How can you do anything without the Peterson?
Yeah, Peterson to dena chahiye, absolutely. Okay, so
should I lecture or shall we?
Yeah. Why don't
get them to bring us some coffee?
No, let's go check on coffee. Oh, hey, acha. I didn't realize this will be useful to have.
Yeah, it's actually very useful sometimes.
Going down is easy.
So I have my Fadi-Bruno's theorem.
Fadi-Bruno.
I think that will take about 40 minutes.
Sounds good. So what should I do? Pause.
Okay, let me just start. If coffee comes.
I'll go check on coffee.
Yeah. Or shall we just go? So, no,
So I paused it. Huh?
yeah,
You just have unpause it.